The Endless Year takes a journey into the science behind the formation of waves. Where do we start from? We can study the science of waves and where do they come from. Do we need wind? What generates these waves? Let's take a look into the science behind this. So how did we get to this stage? How did we get to the stage where we decided to use the ocean as our playground and perform sports such as surfing? This is where we use the wave and its energy to prevail us along the open face, as we can see the surfer here. Wind is created through the constant changes in solar radiation that is causing differences in pressure gradients across the globe. This causes a confused sea, as we can see here. This confused sea is the birth of a wave that is about to travel across the North Atlantic Ocean. The solar heating increases and decreases at different latitudes. More sunlight falls in equatorial regions that are at 0 degrees latitude. This is known as the equinox. Summer and winter solstices occur due to the extreme paths of the sun, known as the Tropic of Cancer and the Tropic of Capricorn. During the summer solstice, it is summer in the northern hemisphere and winter in the southern hemisphere. This occurs on the 21st June. The winter solstice is vice versa, although it occurs on the 22nd of December. The amount of heat radiation is maximum at 0 degrees latitude. Therefore, the cold air at the poles is denser than the warm air from the equator. Thus results in the pressure gradient at sea level being directed from the poles towards the equator. When talking about pressure gradients, we use it in the form of liquids and gases, where gradients reduce flow from regions of higher pressure to lower pressure. However, as we know, the Earth rotates, making the response to these pressure gradients not so direct and simple. Let's move into the structure of our atmosphere. Our atmosphere contains 5 layers: the troposphere, stratosphere, mesosphere, thermosphere, and the exosphere. Let's start off with the troposphere, as this is the layer of the atmosphere that we live in. This layer contains half of our Earth's atmosphere. The troposphere is important to us as it allows us to see and predict what is happening with our weather. As we see here on our illustrated graph of the atmosphere, starting from the troposphere, first layer of the atmosphere, air pressure decreases with altitude. This is because at higher altitudes there are fewer air molecules above a given surface than there are at lower altitudes. Therefore, temperature decreases too, from 17 degrees Celsius to negative 51 degrees Celsius. Most of our weather occurs in this layer. As the height of the troposphere changes between the equator at 0 degrees latitude and 50 degrees north and 50 degrees south of the equator, this transition boundary is known as the tropopause. In the troposphere, the pressure ranges from 1000 to 200 millibars. Also, the moisture concentration decreases with height up to the tropopause. This because the air is much drier above the tropopause. The sun's heat that warms the Earth's surface is transported upwards largely by convection and is mixed by updrafts and downdrafts in the tropopause. The troposphere is 70% nitrogen and 21% oxygen. The lower densities of molecules higher up would not give us enough oxygen to survive here. The stratosphere contains 19% of the atmosphere's gases. However, it contains very little water vapor, and this is where no convection occurs. Also, ozone is created here. Let's take a look at atmospheric circulation around the planet. The rotation of the Earth modifies the pattern of atmospheric circulation in 2 ways. This is known as Coriolis force, discovered by a French mathematician. A deflection of the wind due to slow rotation of the Earth from east to west causes air to be deflected towards the right in the north hemisphere and towards the left in the southern hemisphere. Looking at our diagram, it is evident that firstly, As air moves towards the intertropical convergence zone, the rotation of the Earth will shift the land and ocean underneath it eastward. The result of this is the easterlies, otherwise known as northeast trade winds. Secondly, the roaring 40s creates a band of westerly wind. This band of westerlies is due to the zonal flow at high speed becoming unstable and reshaping air pressure distribution. The outcome of this is air pressure is maximum at mid-latitudes. What is thermohaline circulation? It is the global ocean conveyor belt and is one of the two ways that ocean circulation can be divided into. This is called the thermohaline circulation, which dominates below the ocean surface by a density-driven circulation. Thermohaline circulation is the role of heating, cooling, freshening, and salinification, producing regional density differences within the ocean. Warm water flows poleward near the surface and is subsequently converted into cold water that will sink due to density and flows equatorial. Thermohaline circulation will take 600 years to turn over all deep water in the ocean. During the circulation of this current, we find there are two stages, the cooling of the ocean and the upwelling process in which warm water is driven towards the surface. On the other hand, a wind-driven circulation dominates the upper few hundred meters of the ocean. Here is a detailed diagram of the Coriolis effect. As we can see the differences with and without, it is evident that it would change our climate entirely, as it would become one big convection current if the Coriolis effect was not present. This affects areas such as the doldrums, named after sailors found no horizontal movement of the wind in this area of latitude where the two belts of trade winds meet, neutralizing each other. The birth of a storm is created by an Azores high and Icelandic low, as we can see here. These atmospheric pressure systems influence weather over Europe and eastern North America. During its positive phase, the increased westerlies allow cold air to drain up the North American continent rather than letting it build up and move south. Its pressure gradient becomes stronger, causing storms over the Atlantic. Fluctuations in the strength of these features alters the jet stream. During its negative phase, the pressure gradient is weaker, which results in less storms over the Atlantic. Europe can be seen as cold and dry. Here's a synoptic chart showing the different frontal systems. The large storm sends a solid northwest swell with a long period towards the UK. As we can see, the low pressure system is moving anti-clockwise, whilst the high pressure system is moving clockwise. As the fetch of this storm is large, the formation of wave trains occur. These wave trains undergo movements in order to reach the showing stage. We have the crest, which is the highest part of the wave above still water level. The trough is the lowest point between two successive waves, in other words below still water level. The wavelength is from crest to crest, and if time equals period in seconds. Water waves are also energy waves. The water does not move at the same speed as the energy. The waves move in an orbital motion. An orbital is a package of water that decreases with depth. In deep water, the orbitals remain circular until water stops. In shallow water, the seabed compresses the orbitals. This forms a trichoidal wave, and its characteristics vary on depth plus current. The wind catches through friction on the surface and piles up water into ripples. This creates a rougher surface that increases friction. Wave height and length start to increase as well. Waves with a period of less than 0.1 seconds are capillary waves. Waves greater than 0.1 seconds are known as gravity waves. Here we can view a simulated version of orbital motion transferring energy between the waves. As you can see, the orbitals, the packages of water, get smaller with depth. Any wave that is in water deeper than half its wavelength is a deep water wave. For example, if a wave is 100 meters long and is traveling in water greater than 50 meters in depth, it is a deep water wave. We have many types of wave influenced by different factors, such as the bathymetry, morphodynamics, and of course tides play a huge role in the way a shallow water wave might break. Examples of different types of waves are as follows. Spilling waves. These occur on beaches with a gentle slope. These break further offshore, and these are good for surfing. Surging waves occur where there are a large volume of water that pushes up an embankment. Plunging waves. These are the favorite types of waves to the experienced surfer, and this is where we have a moderate slope. Fourthly, we have rogue waves, which are tsunamis for example, where they are created by disturbances other than wind, for example underwater tectonic plate movement or landslides. Wavelength and depth, and this is of vital importance for refraction. Refraction will bend the crest of a wave until it is parallel to the shore, where the wave cannot be parallel. This sets up longshore drift.